You're able to hear me, right? Good evening. You're able to hear me, no? Okay, fine. Today is the week 12 of the last class of the live interactive session for the NPTEL course and Introduction to Climate Dynamics, Variability and Monitoring. Today, mostly we will be discussing about the various instruments that are used to measure different atmospheric parameters, like the in situ measurements, where we directly come in, the instruments which directly come in contact with the entity or property that we are measuring. And then we have remote sensing measurements, where we measure through with the help of a particular radiation, and we basically measure the reflected, scattered, or emitted radiation from a particular surface, and based on the radiation that we receive, we determine the properties of the surface. And then there are upper air measurements as well, where we get the vertical profiles of the various atmospheric parameters like temperature, humidity, wind speed, etc. So we will be, yeah. So we'll be discussing different instruments that we use in atmospheric science basically today. So we will start. Yeah. Uh, so the first question is, which component of an instrument provides the final readout? So before going into what are the different, yeah, before you're able to see my screen now? Yeah. Okay. So the first question is, which of the instrument provides the final readout? So instrument is basically a physical device or system which is used to measure or monitor a physical variable that is of interest. And the different parts of an instrument includes a sensor that responds to a specific physical parameter that is being measured. And the sensor is usually connected to something called as the transducer, which basically converts the sensor response into a more easily measurable variable. Like, for example, the change in length of a wire into voltage difference, etc. And then we have an amplifier, which is basically used to increase the magnitude of the change that is produced by the sensor. Generally, the change that is produced by the sensor will be very small. So that signal is basically amplified to get a better measurable quantity. And then we have a meter, which can be a digital or analog meter, which basically provides the final readout in terms of magnitude. And then we will have a recording or data backup device attached to this meter. So these are the basic parts of an instrument. It will have a sensor, it will have a transducer, which converts the sensor response into an easily measurable device. measurable variable. Then will have an amplifier, which basically increases the magnitude of the signal that is being measured by the sensor. And then we will have a meter, which basically displays the final readout in terms of magnitude. And then we will have a recording or data backup device, which is attached to the meter. So these are the four different parts of an instrument. So here the question is, which component of an instrument provides the final readout? So which one basically provides the final readout? Yeah, so meter provides the final readout. Meter is the answer. Yeah. Now the next question, what does the dynamic range of an instrument refers to? So when we discuss the how an instrument basically measures a particular variable, the instrument will have something known as a dynamic range and a scale range, which basically gives you how much value the meter can measure. It basically gives you the properties of the instrument, basically like properties of the measurement that is taken by the instrument. So dynamic range basically gives you the range between the least and the greatest value of the parameter that can be measured by the instrument. So suppose you are basically from physics background, so you know like we have the screw gauge, vernier caliper, etc., which is basically used to measure the quantity, which is length, distance, etc. Basically width, length, etc. We use screw gauge, vernier caliper to measure the width of a material. So it will be basically in millimeter range kind of. So like then we have scales which are used to measure like length of some material, which will be basically in centimeters. Then there are things that we measure in meters. Then there are things that we measure in kilometers. So we have like different ranges for each instrument, and based on the scale at which we need the measurement, we use different instruments. So dynamic range basically gives you the range between the least and the greatest value of the parameter that can be measured by that particular instrument. So beyond these values, the instrument reading, it will not change. It will have a maximum value. So we use the instrument to measure a quantity or measure a parameter which exceeds beyond the greatest value that the instrument can measure. Then that value will remain as the greatest value only. It won't detect or it won't show any difference. So dynamic range is usually expressed as a ratio between largest and smallest values the instrument can measure. And there is another important quantity, which is known as the full scale range, which will basically give you the greatest value. So range is basically the difference or the range between smallest and largest value, whereas full scale range give you the greatest value of the parameter that the instrument can detect. So here the question was about dynamic range of an instrument. So the options are the smallest change in parameter value that is measurable by the instrument, the time it takes for the instrument to respond to a sudden change, the range between the least and greatest value of the parameter that can be measured by the instrument, the accuracy of the instrument compared to the calibration standard, the speed at which the instrument's readings are recorded. So which one is the answer? What does the dynamic range of an instrument gives you? So basically, yeah, so it basically gives you the range between the least and the greatest value of the parameters that can be measured. Now, the next question is, we need to find the resolution of an instrument with a full scale range of 100 kilopascal. So what is full scale range? We just discussed. What does full scale range give you? Full scale range, yeah, the greatest value or the maximum value the instrument can measure is given by the full scale range. So here the full scale range is given as 100 kilopascal. So this is some instrument which basically measures the pressure, and it has a resolution of 0.1 percentage of full scale range. And the resolution is given by 0.1 percentage of full scale. So resolution is basically gives you the difference, like how much small of a difference that the instrument can detect. So here it is given as like 0.1% of the full scale range can be detected by the instrument. So if you need to find the resolution, it will be 100 into uh, 0.1. It will be 100, 0.1 percentage, 0.1 by 100. So it will be basically 0.1 kilopascal. The smallest difference or the smallest change that the instrument can detect is 0.1 kilopascal. Correct? Yeah. So yeah, this is again the same thing. The full scale range of an instrument is the dash value of the parameter that the instrument can detect. Full scale range yeah, gives you the greatest value of the parameter that the instrument can detect. Now, the process of comparing one instrument with another whose response characteristics are already known are known more accurately is called what? So different methods are given. So what does it basically? So if we are comparing the response of one instrument with another instrument, what does it basically mean? So this is basically known as calibration. This is the process of comparing one instrument with another whose response characteristics are already known. We already know how one particular instrument respond or the characteristics of that instrument is known. So we basically calibrate a new instrument with that of a already known instrument. So the more accurate the second instrument is called the calibration standard. So the answer to the question will be calibration. Yeah. Now there are different types of errors or uncertainties when we take a measurement using an instrument. So what type of uncertainty is characterized by a consistent repeated offset in the measurement? So basically, uncertainty is the variability of the output value of an instrument. So we generally, so like if while doing experiments, um, we gently repeat the experiment and we note the value that we are getting. So we take more than one reading more than one reading we generally take while doing an experiment to make sure that whatever we are getting is true. So uncertainty is basically the variability in the output values of an instrument on the repeated measurement of the same physical parameter value. Suppose if we are measuring the temperature of a particular object, we take the temperature value multiple. So I'm just giving you an example. If it is not on a controlled environment, the temperature may change. So like suppose consider we are measuring the temperature is not changing and we are taking repeated measurement of temperature of a body. So that the variability when we take the repeated measurement is basically known as the uncertainty. So this uncertainty can be due to different reasons. The first one is systemic uncertainty, which is like there is a consistent repeated offset in the measurement. So we are getting like a repeated offset in the measurement, like a plus two is added each time we take or something kind of like that. So this offset can be generally we can we can correct it by the calibration method. So this is a systemic error that is caused by the instrument itself. So that change will be almost constant. Maybe it will over predict of there will be an over prediction of 2 degree, or there will be an under prediction of 2 degree, or something kind of like that. That too will be a constant. So we can always um, quantify the systemic uncertainties using the process known as calibration. Then we will have random uncertainty. In this case, the variations in measurement will be like it will not be constant. The offset will not be a constant value, but there will be like statistical fluctuations in either the quantity sensed. It could be due to the changes in the quantity that we are measuring, or it could be due to the internal operations of the instrument. So these are very random uncertainties, not a constant thing. So that is random uncertainty. So here the question is what type of uncertainty is characterized by a consistent repeated offset in the measurement? Yeah. So it is basically systemic uncertainty. We always have a consistent repeated offset of the measurement. Now, suppose an instrument takes 25 measurements of a certain variable. The standard deviation of the sample is found to be 4 units. Calculate the standard error of the sample mean. So we know the standard deviation. Standard deviation is given by 4 units. And the number of times the measurement is taken is 25. Now we need to find the standard error. The standard error is given by sigma by root n, which will be 4 by root of 25. What will be the standard error in this case? Yeah, final answer will be yes. So zero point 0.8 is the standard error in this case. Now, which feature is not typically found in data acquisition systems? So what does it mean by a data acquisition system? So data acquisition systems will have a variety of instruments or sensors, which means it basically measures multiple parameters like temperature, pressure, humidity, etc. So the acquisition and storage of data from a variety of sensors is done by a data acquisition system or a data logger. So it will have the different features that these instruments have are like they are programmable and makes measurement either in batches or continuously. They basically take measurements continuously. Like we will have like at a particular or a fixed temporal resolution, you will get the values. And it can acquire data from multiple types of sensor, not a single sensor, but multiple type of sensors will be there. And it acquires data from multiple types of sensors using a multi-way connector block. And it also has a small built-in computer which runs a logging program to determine what to measure and when. Then it also has a computer control switch called the multiplexer, which selects a particular sensor from which, since it has multiple sensor, in order to control that from which sensor we need to collect data, it has a um, computer controlled switch called the multiplexer as well. And this is basically designed to operate with low power requirements, which is like in remote sites where there is not much people around, it can work automatically and have like rugged weatherproof housing. And they usually have an inbuilt clock to time data acquisition events. In order to record this particular measurement has been taken at this particular time, they also have an inbuilt clock, which basically gives you like the time of the measurement as well. So these are basically data acquisition systems. So what feature does not typically found in data acquisition systems is a question. So the first one is a programmable operation, then multi-way connector block for sensor input, analog to digital conversion capability, and the last one is a radio transmitter. Which one is not present in a data acquisition system? So here, if you look at this figure, basically gives you this. Yeah, it doesn't have a radio transmitter. Yeah, it just stores it. It measures data from multiple sensors and then stores the data there itself. We need to like procure the data by visiting the site. It doesn't have a radio transmitter so that it can transmit the data to where we are actually there. Now, the next question: calculate the response uh, minutes for a Stevenson screen thermometer with an A value of 8.2 and wind speed of 2 meter per second. So before solving the equation, do you know what is the Stevenson screen? So yeah. So Stevenson screen is basically wooden box, which is used to house meteorological instruments like thermometers at a weather station. So we will once you start working or once you start doing your research, you will come across what is known as automatic weather stations. So you generally use these weather station data in order to validate your model, or if you are basically doing modeling in order to validate your model, or in order to do analysis of how a particular variable has been changing in the past, and how it is undergoing a change, etc. So the measurements from automatic weather station you will very frequently come through, or you will very frequently use that. So the Stevenson screen is actually a part of the automatic weather station, or it is basically a wooden box where we keep the thermometers. The thermometers will basically give you the temperature value. So this is a wooden box where we basically keep our um, thermometer safe, so it doesn't directly come in contact with the like wind, rain, etc., so that the instruments are kept like safe. So it is basically used to house the meteorological instruments, protecting it from rain, direct sunrise, direct solar radiation, etc. So it will have instruments that basically measure temperature, humidity, atmospheric pressure, etc., in order to avoid the director exposure, like director exposure due to like sunlight, or rain, etc. We generally keep it within a wooden box. So that wooden box is known as the Stevenson screen. It will have multiple instruments that measure multiple. I don't think the figure is clear. It will have instruments that measure the multiple variables like temperature, humidity, pressure, etc. I'll show you a better image, I guess. It will have like different instruments like thermometer, barometer, etc. Not only thermometer, it may contain like uh, oh, this figure is better. Yeah, it's kind of like this. It will have like multiple instrument kept inside. It's kind of like a wooden box. So this one only contains different types of thermometers, but it may contain other instruments as well. So here the question is calculate. So it has proper ventilation. So vent will pass through it actually. Calculate the response time in minutes for a Stevenson screen thermometer with an A value of 8.2 and wind speed U of 2 meter per second. So the response time tau is, yeah, A is basically a constant. A by U is the equation. Yeah, A is basically a constant value, which is uh, which is given as 8.2, and the wind speed is given by 2 meter per second. The equation tau is basically A by U raised to A by U raised to N. N is 0.5 and A is 8.2. So tau will be 8.2 and U is the wind speed. Wind speed is 2. 2 raised to 0.5. What will be the answer? Uh, yeah, I think the options are given in minutes. 4.1 second. Yeah. We need to find the answer in minutes actually. So once you convert it into minute, I think it will be rather less. 8.2 divided by 2 raised to 0.5. So yeah. So it will be, sorry. Yeah, 2 raised to n. N is 0.5. Yeah, the answer will be in meters actually. How much you're getting? 8.2 by 2 raised to 0.5. Yeah, the answer will be in meter. The answer is 5.8. No, answer will be in minutes actually. Yeah, wind speed will be in meter per second. And the equation basically gives you the response time in minutes. Like it depends on the unit of A and N as well. Yeah, the answer will be 5.6. Yeah. The next question is a humid cap has a linear relationship between capacitance change and relative humidity change. So what are basically humid cap? So humid caps are basically used to measure relative humidity. So these, how do they measure relative humidity is basically by the changes in capacitance. So humicaps are sensors that respond to relative humidity changes by changes in capacitance. They are basically made up of capacitors with porous dielectric material that absorbs water and that basically have a relationship with relative humidity change, and it has a very slow response time of approximately 10 to 100 seconds, and the response time increases at very low temperature. So it basically has an upper electrode and a lower electrode, um, and in between they have a very thin polymer frame, and the difference in the capacitance between these two electrodes will give you um, the relative humidity change during that particular time. So the question was, a humid cap has a linear relationship between capacity change and relative humidity change. Is it true or false? Yeah, it is basically saying that it has a linear relationship with relative humidity change. So the capacitance is linearly, or the changes are almost linear. The capacitance difference will basically gives you the change in the relative humidity. So the answer is true. Sorry. Uh-huh. Okay. Okay. Once it absorbs water, like, okay, is it instantaneous or does it continuously measure? Mm, Let me just see. I'm not sure if it's how does it measure continuously, or it just gives you like one. No, based on the humidity change of the atmosphere, it absorbs and releases water vapor. So humidity is less, then it will release water vapor, and if it is more, it will absorb water vapor. So that's how the electric properties changes. It can release also. Both will happen. It absorbs or releases based on the humidity, atmospheric humidity. So that's how it measures. Okay. Now, a Q pattern barometer is a type of aneroid barometer. So, what is basically a barometer? You know, what does a barometer measure? Yeah, barometers basically measure pressure. So we are familiar with the mercury barometer, where we have a dish of mercury on which we have an inverted test tube. So based on the pressure that the atmosphere exerts on this dish of mercury, the mercury level in the inverted test tube increases, and based on the height at which the mercury has increased, we measure the pressure. So that's how we measure pressure using a mercury barometer. Um, and a Q pattern barometer is a commonly used type. It contains a mercury storage cistern, a vernier scale, and a thermometer for temperature expansion correction. So, based on the temperature, the mercury may so the temperature changes should not affect the pressure measurement. So, in order to correct for the temperature expansion, it also has a thermometer, a vernier scale, and a mercury storage system. So, a Q pattern barometer is a type of mercury barometer. So, the question was a Q pattern barometer is a type of aneroid barometer. So now we know that a Q pattern barometer is a type of mercury barometer. Now, what does it mean by an aneroid barometer? So aneroid barometers basically uses a thin metal chamber or diaphragm with a membrane which deforms under pressure differences. So the deformation can be measured mechanically, and so we have basically a thin metal chamber or diaphragm which has a very thin membrane which basically deforms under pressure differences. The metal capsule or diaphragm is evacuated, and the elastic modulus allows it to distort by atmospheric pressure changes by a repeatable amount. And this, yeah. So, in case of mercury barometer, we basically measure the pressure by, yeah. We basically measure the pressure by measuring the height up to which the liquid column has raised. Whereas in case of an Android barometer, we measure the changes in the deformations of a metal chamber or a diaphragm. Based on the pressure, the diaphragm or the metal chamber deforms, and based on the deformation, we measure the pressure. That's how an aneroid barometer works. And again, aneroid barometer has also has two types. One is like which has a very flexible diaphragm sensor. This again basically detects the changes in the diaphragm, flexing of a diaphragm, and the associated change in capacitance caused by the separation of the diaphragm and the metal plate distance basically gives you the pressure difference. So the pressure is basically measured through the capacitance difference. And then you have a vibrating cylinder barometer. This sends pressure based on change in the frequency of a thin-walled cylinder whose insides are open. So like you can see here, this as the cylinder, based on the oscillation frequency of the thin-walled cylinder, whose insides are open to the atmosphere. The oscillations basically gives you the oscillations basically gives you the pressure difference. Number of oscillations basically gives you the pressure difference. So in case of Android barometer also you have it oscillates based on the pressure actually. Like the oscillations are a proxy to the pressure differences. How does it? The oscillation is actually it is an oscillating cylinder. The oscillation is actually a yeah, it is why it basically so the cylinder has a natural resonant frequency. The changes in the natural resonant frequency is um so inside of the cylinder the vacuum is between the cylinder walls actually. Like it has two layers. No? So between the cylinder layers there is a vacuum, but within the cylinder is actually open to the atmosphere. The cylinder basically vibrates according to the pressure. That's how it has been designed, I guess. So the vacuum is between the cylinder walls. Between the cylinder walls, a vacuum is no. It's this the cylinder has two layers, no, like as you can see here. So like between the walls, this is vacuum. So this is the cylinder as such, like this. So the cylinder between the cylinder layers is vacuum, and this is the inside of the cylinder. This is open to the external atmospheric pressure. So cylinder basically have a frequency which is a proxy to the pressure changes of the outside actually. So it is basically allowed to resonate at its natural frequency. So if we see any changes in the natural frequency of the cylinder, that change basically gives you the external pressure. That is the basic idea. Uh, yeah. So the change in the resonant frequency of the cylinder basically gives you the pressure difference. So it is allowed to oscillate in its natural frequency. So whatever changes are actually happening to the natural frequency of the cylinder will basically gives you the external pressure. So that's how it works. That is vibrating cylinder. Sorry. Okay, okay. Ha. I think it is the it is a stable material. Yeah, nickel ion chromium alloy is used actually. So yeah, ion chromium, nickel ion chromium is used. Stable nickel ion chromium alloy is used actually. Maybe like which has like very low reactivity with the atmosphere. Like the changes in the atmosphere, like the humidity and all those changes should not affect the material. So that's why they have used like highly stable material. Like they are basically using stable alloy actually, so that it doesn't the material doesn't react with the surrounding. Nickel ion chromium alloy is used for the cylinder material as the cylinder material. Anyway, the question was like a Q pattern barometer is a yeah. Yeah, the answer is false. This is basically a, mercury barometer, not the aneroid barometer. Now we are going to anemometers. Do you know what does an anemometer measure? Yeah, anemometer basically gives you the wind direction and wind speed. Sorry, sorry. Okay, huh. A cup anemometer always rotates in one direction. The answer is true. So, a cup anemometer basically has three conical or hemispherical cups at the equal distances from a vertical shaft. So, you have like a vertical shaft kind of like this, and then you have three um, cups which is connected with a metallic. Yeah. So, it has a vertical shaft and three conical or hemispherical cups at equal distances from the vertical shaft. The vertical shaft, this is free to rotate um, to cause little or no mechanical loading, and the cup arrangement is asymmetric to ensure that the anemometer rotates only in one direction. So yeah, the anemometer only rotates in one direction. And in the anemometer, like in this wind measuring instrument, there is another thing known as the wind vane. So these cups basically gives you the cup anemometer, and the wind vane is basically a flat vertical plane attached to a horizontal arm. This is able to rotate on the vertical shaft. So the question is, a wind vane always rotates in one direction. Is it true or false? So, yeah. Because as you can see, it doesn't, it can rotate in all directions. Like whatever direction the wind is coming, this arrow will basically point to the wind direction. So if the wind is pushing it from this side, it will move like that. And if the wind is pushing from the other side, it will move to this side. So this is free to rotate in both the directions. And the direction at which this arrow points will give you the wind direction at which the wind is blowing. This basically gives you the wind direction. So this is wind vane. This aligns with the wind. Yeah, yeah, yeah. The dynamic pressure of the wind is equal to 0.5 rho u square. Lecture video. Okay, how does it came is not explained. Okay. I think rho is the density of air actually, and v is the wind speed. This is basically kinetic energy per unit volume. Yeah, kinetic energy is uh, half mv square, right? Mass can be written as density into volume. So, like if volume is unitly, it will be half rho v square. Yeah, Newton per meter square. Yes, the unit will be Newton per meter square if we equate it. It basically gives you the pressure. Force per uh, unit area is pressure, right? Force into distance is energy. Work done. Force by area gives you the pressure into distance. Uh, Kinetic energy is basically given by half mv square, right? Where mass is basically density into volume into v square. And force by area is pressure. F into dx is work done or energy, right? So if it is unit volume, it will be half rho v square. Maybe unit distance it is considering, so you will get the dynamic pressure. Maybe it's not the it is dynamic pressure, not the actual pressure that we. What is the equation for a dynamic pressure? Yeah, dynamic pressure is basically dp by dx. Change in pressure with respect to distance. If you do dx, then it will be like you'll get no. This will be F by A. So if we are taking the change in pressure dp, dx will be F into dx is energy. Yeah, area into distance. Yeah, if we multiply dx on both sides, I think it will be fine. So it is basically dynamic pressure. Okay. Force into dx is energy. Okay, you're telling here dx won't come. Okay, here area. Force into dx is energy, right? F into dx is half rho into volume into v square. Now yeah, if we take energy by volume, yeah, exactly. Then it will be fine, right? F by A into dx will come. Then it will be pressure. It will gives you pressure, right? Pressure is equal to half rho v square. Correct? Oh, So yeah, I think that's how it came. And I think dynamic pressure is given by dP by dH as well. Okay. Now the next question. In a sonic anemometer, the separation distance is 10 centimeter. It takes 30 microseconds for the sound to travel forward and 40 microseconds for the sound to travel backward. The sound speed in this direction is dash. That is the question. So this is the figure of a sonic anemometer. As you can see here, it has two transducers, one at top and one at bottom. So we basically this is used to calculate the wind speed. So for sound to so if we sound is traveling from this transducer to this transducer, the speed at which or the time the sound takes to reach um, to travel this much distance is dependent on the velocity of the wind as well. So based on that, we can calculate the time that the sound takes to reach from this transducer to, or the time it takes will help us to get the velocity of the wind. So the time required for pulses of ultrasound to travel forward and backward between two fixed transducers, which is separated by a length of 10 to 20 centimeter is measured. We basically measure the time and the forward flight time is given by 1 by Cs plus V and the backward flight time is given by not 1 L by Cs plus V where L is the distance separating the two transducers. Forward flight time is L by Cs plus V where Cs is the velocity of the sound and V is the wind velocity and the backward flight time is given by L by Cs minus V. Now, once you know T1 and T2 and the velocity of sound, we can measure the wind speed, which is given by 0.5 L into 1 by T1 minus 1 by T2, where Cs is basically the speed of sound and L is the separation distance in meters. Now, in the question, it is given that L is 10 centimeter and forward time is given as 30 microseconds and the backward time T2 is given as 40 microseconds. The sound speed, we need to find Cs. We need to basically find Cs. So if we want to find Cs, you need to know what is V. Either from T1 or T2 we can get Cs, but initially we should know what is the value of V. So first we will find the value of V, which is 0.5 L into 1 by T1 minus 1 by T2. So V or the velocity of the wind is given by 0.5 L by 1 by T1, which is 30 microsecond, and 1 by T2, which is 40 microsecond. We need to find the speed of sound in meter per second. So we can convert it into, this is 30 microsecond. Both is micro. I think it will be 10 raised to 6. So 0.5 into L is given as 10 centimeter. Hmm, and by 30 into 10 raised to 6. How much it will be? What will be the wind velocity? Hmm, 417. In order to find the speed of sound, we can use T1 is equal to L by Cs plus V. L by Cs plus V. T1 into Cs plus V is equal to L. T1 is basically 30 microseconds. 30 into 10 raised to minus 6 into Cs plus V is 417 is equal to L. L is 10 centimeter minus 2. Yeah, I think something is wrong. Where did where did I make a mistake? The value is very high, right? This also doesn't make much sense that the velocity is 417 meter per second. That is very high. The answer is 8 meter per second actually. The time is given in microseconds. The answer is supposed to be 8 meter per second. I'm not sure where I'm doing it wrong. This is the answer. 8 meter per second is the answer. Try to solve it. Yeah, that's what. I don't know where I'm. Somewhere we are doing wrong. We open the bracket here itself. That should be the same one. Cs into T1 plus V into T1 is equal to L. Simplifies Cs is equal to L minus T1, L minus V T1 by Cs, which will be 10 into 10 raised to minus 2. Huh? Maybe. Not sure. I think something is wrong. Either we are doing something wrong or something is wrong with the question. Anyway, try to solve it later and just let me know where we are actually wrong. I'm not sure. Anyway, the answer is given as 8 meter per second, and these are the equations that should be used. I hope the equations are clear and the concept is clear. Fine. Anyway, fine. Now the next question is, yeah. The angle the wind vane is making with the north is 120 degree and the cup anemometer reading of wind speed is 6 meter per second. Its zonal component value is. So do you remember what is zonal and what is meridional? Zonal is in which direction? Huh, huh. South to north is meridional. West to east is zonal. Now, the question is the wind vane is making an angle 120 degree. With the north, it is making an angle of 120 degree. I think like this. Is making an angle 120 degree with the north, and the cup anemometer of wind speed is 6. And the cup anemometer reading of wind speed is 6 meter per second. U is 6 meter per second. We need to find small u or the zonal wind component. The zonal wind component is given by minus u sine theta. The zonal component of the wind speed is given by minus u sine theta, and u is minus 6 into sine 120. How much it will be? Minus 5.2 meter per second. So minus 5.2 basically, negative basically means what will be the direction of the wind? Yeah, so that's why it is kind of southeasterly the wind is blowing. It is east to west the wind is blowing. That's why we have this negative. So the answer is minus 5.2 meter per second. Now, so as we told, anemometers are basically used to measure the wind speed and wind direction. Now we are moving to measuring the radiation. So a radiometer is the instrument that basically measures radiation, and it basically has a thermopile which converts the electromagnetic energy into the thermal energy of an exposed absorbing surface. So if we have a surface which is exposed to the incoming solar radiation or which is exposed to the radiation, we will measure the temperature of the exposed surface and we compare it with the temperature of an unexposed surface. And but the temperature difference basically gives you the radiation that has been incident on that particular surface. So this is basically measured using a set of thermocouples connected in a series. So thermocouples will give you the temperature. So thermopile is basically used to measure what? Yeah, or it basically measures the temperature. One thermocouple measures the temperature. So if you have a series of thermocouple connected, each will give you the temperature of that particular surface. So exposed surface minus unexposed surface will gives you the radiation. So that is thermopile. So thermopile, sorry, that connect, yeah, connected in. Yeah, thermocouple is a single instrument actually. It is connected to another thermocouple. Like two or three thermocouples will be connected in a series. Different temperatures, yeah, based on its exposure to the radiation. Yeah. Now the next question, and so here the answer is temperature. Yeah, we told. An instrument used to measure direct beam solar radiation. So there are different types of radiometers. So we know that we have incoming solar radiation, we have outgoing solar radiation, we have a little bit amount of incoming. Yeah. How to? How? I think once or twice when you go through, I think you will get an idea kind of. I don't have a shortcut to remember these things. You have to read only. I think this Pyrilio, sorry, the Pyrilio Pyrano. I think helio you can connect it with uh, sun, I guess. Meter is basically direct solar radiation. Pyrilio, Pyrano. Photometer anyway you can connect it. Photometer basically is visible only. So that I think is easy. Like photometer will basically measure the visible part of the spectrum. Albedometer, as you know, like received by reflected from a surface. Pyre Geo is also easy because Geo is basically the terrestrial radiation. So Pyre Geo will give you the terrestrial radiation. And I think infrared thermometer, so basically Earth emits radiation in the infrared range of the spectrum. So an infrared thermometer will basically measure the long wave radiation, like which is being emitted from an object or from the surface of the Earth. I know there is no shortcut, I guess. These are simple methods with which you can just connect things. PyRGO, I think you can connect it with Earth. So it basically gives you the terrestrial radiation. And again, infrared is the range in which the Earth emits radiation. So you can connect like it is basically showing the long wave radiation being emitted from an object. And helio, you can connect it with sun. So like solar radiation that is coming from the solar beam, kind of like that. I uh, pyranometer gives you diffused shade ring pyranometer gives you diffused solar radiation. Not direct solar radiation, but diffused solar radiation. And pyranometer, I think, gives you the direct solar radiation, global solar radiation. Shade ring is diffused solar radiation. It doesn't receive direct solar radiation. It is actually placed below a shade or something, so it basically gives you the diffused one, not direct one. So that is shade ring pyranometer. Pyranometer, yeah, pyranometer measures all global solar radiation. Yeah, both direct and diffused, whereas shade ring pyranometer mostly measures diffused solar radiation. Yeah, so the question is which instrument used to measure direct beam solar radiation? Direct solar radiation is measured using, yeah, pyrheliometer basically measures direct diffused solar radiation. Yeah, an instrument that used to measure diffuse solar radiation. Yeah, shade ring. So which of these is not a reason why a glass enclosure is not used for a pyranometer sensor? Which could be? So it should not. In order to prevent the diffuse shortwave radiation from prevents thermal radiation losses from the sensor surface. Yeah, third one, right? Prevents no, it basically measures the diffuse radiation. No, it is measuring the diffuse shortwave radiation, right? So if you have a glass surface, it will like hit and then reflect back. No, it is coming. No, it will prevent it to entering the sensor surface or short. Yeah, we are measuring shortwave only. Diffuse shortwave radiation we are measuring. So it will, if we have a glass surface, it doesn't glass enclosure. It will not allow the diffuse radiation to enter the sensor, or it will prevent the shortwave radiation from hitting the sensor surface, right? So it basically affects the diffuse shortwave radiation only that we are trying to measure. Thermal radiation is after reaching the sensor what it re-emits. Yeah, option C is correct. Prevents diffuse shortwave radiation from hitting the sensor surface. Which of these require a pair of pyranometers to be used? So what is a pyranometer? Pyranometer measures. Yeah. Pyranometer measures the shortwave flux, right? Global shortwave flux. Which of these require a pair of pyranometers to be used? The albedo meter requires a set of pyranometers to be used because you need to know how much is incoming to measure the albedo. So it basically gives you the albedo of a particular surface. So in order to find that how much is being reflected back, we should know how much is coming. So in order to find the solar radiation that is incoming or the incoming solar radiation flux, we use the pyranometer. So the answer is albedo. Yeah. Polythene sheet covering is used in which instrument? So the pi radiometer basically uses a polythene covering. So pi radiometer, what does it measure? Yeah, it basically measures the thermal radiation. Huh. Mm. Yeah. So pi radiometer is the correct answer. No. A tipping bucket rain gauge. So tipping bucket rain gauge basically measures rainfall that is received um, over a particular region. So tipping bucket is basically an instrument. Is a bucket which is, I think I'll show you the figure and it will be easier. So tipping bucket once the bucket fills up, it basically tips and gives you the rainfall. So based on number of times the bucket has tipped, you can find the rainfall that has happened over that particular region. So once it fills, it kinds of drains. After it fills up to a particular level, the rainfall kind of drains. Yeah, yeah, just so it has a bucket kind of like this and like a seesaw kind of thing inside. So once the rainfall fills over this particular region, then it will be drained to this particular uh, bucket or something. So based on the number of tips that is happening, we can calculate the rainfall that has happened over that particular period of time. So basically here the question is given as a tipping bucket rain gauge has buckets of 2 millimeter depth. So once the bucket fills up to 2 millimeter, it will tip. Over a 3 hour period, 3 hour period, it registers 30 pivots in total. So over a 3 hour period, the tipping bucket actually registered 30 pivots in total. So 30 times the bucket tipped and the water drained. So what will be the average rainfall rate in millimeter? That is the question. Uh, so the total rainfall depth is basically given by the NB, which is number of times the bucket tipped into the depth of the tipping bucket rain gauge, which is 2. So this will be P is basically given by the average rainfall depth is given by 30 into 2. Like how much rainfall actually happened is given by 60. Yeah, 60 millimeter is the average rainfall depth. And the question is to find the average rainfall rate. To find the average rainfall rate, it is given by the total rainfall depth divided by the time, just Tn minus T1. Or here we have like over a period of 3 hours. So T1 is 0. If you take, it will be 60 by 3 hours. We need to find in millimeter per minute. 3 into 60. So it will be, yeah, 1 by 3 millimeter per minute is the average rainfall rate. So this much rainfall happened. This is the like per minute. This is the amount of rainfall that has happened. So that's how a rain gauge gives you the measurement of rainfall. Now, a hypsometer. What is a hypsometer? So hypsometer basically measures this again measures the pressure. Yeah, hypsometer gives you the boiling point temperature of a liquid at that given pressure. So this is basically used to determine the pressure actually. It measures the boiling point temperature of a liquid. Hypsometer, boiling point temperature of a liquid. And we use this boiling point temperature of a liquid in order to find the pressure at that particular point. So this is used to determine the pressure by correlating the change in the boiling point temperature of a liquid with change in pressure. So we basically use it to determine the pressure. Even though it measures the temperature of the boiling point temperature of a liquid, we basically use it to determine the pressure by correlating the change in the boiling point temperature of a liquid with change in pressure. That is hypsometer. Now, what is the task of a modem in the radio sonde instrument package? So, do you know what is a radio sonde? Yeah. So, radio sonde is basically it will basically have a balloon, either filled with hydrogen or helium. Then it will have a small box which will have different instruments to measure different atmospheric properties like temperature, pressure, humidity, etc. And then it will have a small modem connected to it so that we can transfer the measurements that is being recorded during the flight of the radio sonde to the ground, to the receiving device in the ground. So this is the balloon. It will be either filled with helium or hydrogen, which are like very light elements. And then it has a parachute kind of thing. So what happens is that as it goes up in the atmosphere, what will happen to the pressure? Pressure decrease. And what will happen to the volume of air within the balloon? If the pressure decreases, it will expand and eventually it will, yeah. So as we go up in the atmosphere, this hydrogen or helium filled balloon, as the pressure decreases, after reaching a particular height, the balloon explodes. And once it's explode, it should not fall directly to the ground. No, because it is very dangerous. So there is a small parachute attached to the radio sonde so that once the balloon explodes, it slowly lands on the ground. So generally these instruments are not recovered after the launch of radio sonde. It is like single use. Once you launch the radio sonde, the instruments that we are attaching with it is lost like permanently. We don't know after launching the radio sonde where it will land once the balloon explodes. So generally, it is very difficult to recover the instruments that are connected to it. But I think recently there have been what you say there have been they are trying to recover these instruments as well. Recently I have seen like attempts to do that. So generally the idea is that the parachute is there because once the balloon explodes, these instruments will slowly land on the ground without causing much issue to the people. So this is how, and as the balloon, during its ascent in the atmosphere, it measures temperature, pressure, and humidity as it goes up, and we will get a temperature profile, vertical profile of different atmospheric parameters like temperature, um, density, like temperature, density, humidity, pressure, etc. So this is basically used for vertical profiling to get the vertical profile of the atmosphere. So that's how why a radio sonde is used, and it will have a modem in order to transmit the radio signal. Whatever is getting measured is actually getting transmitted to the ground receiving station. So that's why we have a modem in the package. So the answer to the question is it will be like single use only. It like generally no, yeah, it is costly. Radio Sunday launching is a bit costly. Generally the instruments are lost actually after we launch the Radio Sunday because we don't know where it will fall off. So we generally lose the instruments. Yeah, like only the balloon will burst. All other things will come back to the ground itself. The balloon, once the balloon bursts, the whole thing as a group will come down and reach the surface. So either it can land on the ocean or it can land on the ground also. Sorry, I think it is transmitting the data that it is collecting using radio waves, I guess. That's why it is known as radio sound. And it is used for atmospheric sounding or atmospheric profiling. That's why radio sounding. Yeah, so what will be the answer to the question? Yeah, the audio one. No, no, it is used for transmitting the radio signal. The modem is used to transmit the radio signal. So whatever we are measuring, we need to transmit it to the ground receiving station. So the modem, the purpose of modem and the radio sound is actually to okay. Antenna is used to. So the digitized information. So it does both actually. It converts the no, it basically the measurements are actually converted to digitized information, and the digitized information are sent over the radio channel via the modem. So the modem transfers the measured quantities through a radio signal to the ground receiving station. It also converts both the does at once digitize the measured quantities and then it transmits it to the ground receiving station. Both it does. We don't need an audio tune. What will we do with the audio tune? We need like the digitized information of the measurements. No, but we can't do anything with the audio signal. No, the purpose is to get the measurements of the temperature, pressure, and etc. So the purpose is not to send an audio signal. We need the data that is being collected by the sound right? So the modem digitizes the information of the measured quantities and it sends the information through the radio channel. So that's what the modem does. Okay. So the next question. So now we are moving on to, so now we learned about what are in situ instruments like thermometer, which is used to measure temperature, barometer, which is used to measure pressure. Then we have hygrometer, which is used to measure humidity. Then we learned about anemometer, which are used to measure wind speed, and wind vane, which is used to measure the wind direction. Then we also learned of different radiometers like pyranometer, pyrheliometer, pyrgeometer, etc., which are used to measure the different radiations like incoming solar radiation, outgoing long wave radiation, incoming diffuse radiation, etc. So we learned about all these things. So all these are in situ instruments or upper air measurement instruments like the radio sound. So now we are moving on to remote sensing, where we doesn't directly come in the instrument doesn't directly come in contact with the um, property or with the surface that it is the property that it is measuring actually. We are using radiation to measure the properties. So the first question is the remote sensing applications usually measure properties of surface. Is it true or false? Yeah. Now, in which of these requirements one should not use remote sensing or remote sounding technology? So the use of remote sensing is that we can have a coverage, wide spectrum of coverage we can have, and there are its demerits also, like in terms of the temporal and spatial resolution. So the purpose is to get a wide spatial coverage. So they among these options, which one for which requirement, we should not use a remote sensing technology. So the first one is land surface temperature data is to be acquired over the entire Asian continent over a 10-year time span. Second one is vertical species concentration profiles over the entire subtropical troposphere is to be acquired over several years. The third one, very accurate surface temperature data over a specific geographic location is to be acquired. The fourth one, distribution of clouds over the Pacific Ocean was required for a period of several years. So, which one will be the answer? Which one we should not use remote sensing? Yeah, because yeah, we need very accurate surface temperature. That also it's just a very over a specific geographic location. So it is more easier to use an in situ measurement device. Now, which of these are true for satellites on a sun synchronous orbit? So, do you know what is a sun synchronous orbit or sun synchronous satellite? Sun synchronous satellite measures, sorry, yeah, okay. Geostationary satellites gives you over a particular geographic location. The geostationary satellite moves along with the Earth. It gives you only over a particular location. So sun synchronous satellite is a low orbiting satellite. You know that the geostationary is actually at a height of around 36,000 kilometer, I guess. So this is over a small, it is not over that much height. This is over like 600 to 800 kilometer height only above the surface of the earth. And it gives you data over multiple locations, not over a single location. It gives you data over multiple location. And it always measures data at the same um, like what you say sun synchronous in the sense it measures data over the local time over a particular region. Yeah. So it crosses the same latitude in the same sense at the same local time, and it has a greater coverage of the earth's surface. I'll show you the figure. I think I'll show you a video. Just a second. I think that will be better. So, so it kind of takes rotation like this, like from north to south pole. This orbit kinds of keep moving. As you can see, that blue line is actually the area that the satellite is covering. So based on as the Earth is rotating, we will eventually get the full coverage of Earth. So the orbit is kind of changing as the Earth is rotating, and eventually we will get the full coverage of the Earth. The orbit kind of keeps on changing. Like it basically moves along with the sun. Like during a day, it moves along with the sun. So that's why we get the measurement at the same latitude at the same local time. So the question was which of these. Yeah, if you look at the project, look at how the satellite moves in the along the longitude, it will be like this. It basically covers the whole. We will get data over the whole longitude like this. There will be multiple orbits. The frequency or the temporal resolution at which it provides will be different. Or it is not like in a year, like it basically moves along with the sun or along with the sun's. So you can get like data over a particular place at a particular time. I think maybe the temporal, it is not over a year. It doesn't take 1 year to complete the whole, what do you say, to cover the whole earth. Haha. Sun is like we have day and night, no? Earth takes 1 year to, so, so that basically differs actually. It is not a year. No, no, it depends on the what is the speed at which the satellite is revolving actually. Sun synchronous in the sense it visits the same time at the same local. Every day it visits the same spot. Not every day, like it visits us. So suppose India, it is giving you measurement over India at 10:30 a.m. local time. So the next time that that the satellite visits over India, it will be at the same local time. It will be again at 10:30 a.m. So it may take like not I think the resolution will be the temporal resolution will be different for different satellites. You can't give you so some satellite may take 8 days to cover the whole Earth, and then again it will start doing the orbital like, orbit again, like that coverage again. Some may have more of a higher temporal resolution. It won't take 8 days kind of. So it depends on the satellite that we are considering. It's not like it doesn't take anyway a year or such months to take the measurement over the same location again. So generally, we have a satellite known as MODIS. It gives you the data over India like every 8 days. So it has an 8 day composite. It just means that it visits the same latitude at the same local time every time it is. So if it is giving the data at 10:30 a.m. over India, the next time that it will be over India, it will be at the same time, like 10:30 a.m. So maybe today you have the data, then after 8 days again it will visit and it will be over India at the time 10:30 a.m. That's the whole idea. So it's the same location in the same local time, and it basically has the coverage of whole Earth. As it revolves, it basically gives you the coverage of whole Earth. Yeah. So it crosses the same latitude at the same local time, and yeah, has the greatest coverage of the Earth's surface. B and D is the answer, right? Yeah. Okay. Now, geosynchronous satellites have excellent spatial resolution. Is it true or false? So, can you tell me, compared to the true? Yeah, yeah. Geostationary will have a like very low resolution, but the geosynchronous satellites have very high spatial resolution. Now, push broom imaging system is used for. Um, so, what does it mean by a push broom? So, as we said, like as the satellite, how does the satellite measures data over the surface? So, there are different techniques by which it measures. So, suppose we have a sensor on a satellite. So, suppose this is the sensor. So, this is Earth. So this will have either it will measure in a 2D structure, like it will have a spot like this. So the data over this, so this, if this is a projected area that the satellite is looking at, it can measure a 2D, it will get a 2D image kind of like this, like XY kind of an area it will measure, or otherwise it can it will be having a linear detector kind of thing. So it will be measuring linearly, not a 2D only, but like it will be giving measurement along a single line only. It will be like this also. So like there are different ways in which a satellite measures. So it can be along a single line or a zero. Yeah, yeah, yeah. So, zero D detector. Okay, it is a single point sensor, like not along a line, but just a single pixel it will measure, I guess. Like it will be just a single box it will measure. Like here you have multiple boxes. Here you have like along a linear line, you have like multiple pixels. This is basically not a pixel. Like this box will be a pixel based on the spatial resolution of the satellite. Now, zero detector will only measure one pixel at a time. So linear detector will give you along a line, and then 2D detector will give you a box of x and y dimensions, whereas a zero detector will give you just a point or a single pixel at a time. The question is the push broom imaging system is used for a 2D detector, a linear detector, a geosynchronous satellite detector. So in case of a 2D detector, you have an image like this at once, and as the satellite moves, you will have another image like this. So this will be covering. So the Earth is also moving, right? So now you have data over this. Once the Earth moves, you will have data over another location. So this is how a 2D detector works. And in case of a linear detector, what happens is that the sensor itself moves. So once it measures the data over this region, the sensor moves to this region and then measures the next line. This is basically known as push broom imaging system. The sensor moves and then takes data over multiple lines, along multiple lines. So this is basically used in what will be the answer? Yeah, So this is basically used in a linear detector. The sensor itself moves and then measures over multiple lines. The next question is in VNIR. VNIR is visible near infrared range. So we have sensors which emit radiation at different wavelengths. So the measurement of the emitted radiation using different wavelengths gives you properties of different the radiation characteristics that is received or reflected from different materials will help you to detect the properties of the material. That's how it basically works. So in visible near infrared image, so we have different sensors with so we have thermal infrared imaging. We have visible near infrared imaging. So like all these are used for different for measuring different parameters. So in case of visible near infrared image, a pixel has high reflectance in the visible region and very low reflectance in the near IR region. The region is likely to be what? That is the question. So when we use this visible near infrared imaging in climatology, so we generally use this for constructing land use land cover data sets. Land use land cover in the sense by looking from the satellite, we can find which region is actually a forest, which is a city, which is a water body, which has vegetation, kind of like that. So that is basically what a land use land cover data set gives. So visible near infrared images are used for land use land cover classifications. So suppose VNIR image uh, has high reflectance in the visible region. So whatever is being emitted from the visible region is showing very high reflectance. Whereas in case of near infrared region, it is having very low reflectance. So from this characteristics, we need to identify what particular land cover that we are dealing with. So the detection basically depends on the reflectant properties of various wavebands. For example, if a pixel is showing low reflectance in a pixel is showing low reflectance in visible and high reflectance uh, in near IR. This basically means that you are encountering a vegetation, green leafed vegetation. So low reflectance in the sense it absorbs most of the visible radiation that is incident on it, whereas it is reflecting back the near infrared radiation. So that this basically shows corresponds to vegetation. Now, a pixel that shows high reflectance in visible, we know that the solar radiation peaks in the visible range of the spectrum, right? Around 500 nanometer, we have already learned. So if a material is having very high reflectance in the visible and very low reflectance in the near IR, then that is basically snow cover. Yeah. So here the question is high reflectance in visible and low reflectance in near IR. What will be the answer? Yeah, it will be land area. So in case of barren land, yeah, in case of barren land and water bodies, so it barren land basically shows high reflectance in both visible and IR spectrum. And water bodies, I think, will be having very low reflectance in both because it mostly absorbs most of the solar radiation. So in case of barren land, it will have high reflectance and both visible and near IR. And in case of water, low reflectance and visible, whereas nearly zero reflectance and near infrared. Low reflectance, visible, and nearly no reflectance in the near infrared region of the. So that's how. So basically, remote sensing people know like how to detect, how to convert this values into different land cover types. So I think I'll just we don't have much time, so I think I'll solve one problem and then we will end the class for today. If you have any doubt or anything, you can always. When is your exams? Did the date came? Okay, 26th October. Okay. Mhm. Book. You can go through the the materials that is provided in the class only, I guess. I guess so because most of the assignment questions are from the um what you say from those materials only. So if you want to read more, if you want to read more about thermodynamics, then there is a book called Wallace and Hobbes, Introduction to Atmospheric Thermodynamics by Wallace and Hobbes. And if you want to read about atmospheric physics, there is a book called Meteorology Today. Uh, that is very helpful. I'll show you just the cover page if you want. So these are the books that I have. Uh, sorry. Yeah, that's what I was just looking. Meteorology Today is written by. Yeah, Donald Ahrens and Robert Henson. Donald Ahrens. Donald Ahrens. I think I'll type in the. Yeah, I'll type. Hmm. So one will be Introduction to Wallace and Hobbes. What is the book title? Introduction to Atmospheric Science. Yeah, Atmospheric Science, an introductory survey by John Michael Wallace and Peter V. Hobbs. Atmospheric Sciences, an introductory survey by John M. Theta V hops. And then meteorology today. I think these books might help. Wallace and Hobbes is very good for atmospheric thermodynamics, and meteorology today gives you like basic idea about everything. Like it's kind of an introductory book, like the atmospheric structure, that Milankovitch cycle we discussed, etc. So I think these two might help. So should we solve this problem or should we just stop here? You want to solve it or let's wait? Yeah. So the question is, a thermal infrared imaging system uses the two look. You told to solve it, right? Or you'll solve it. Yeah. A thermal infrared imaging system uses the two-look technique to determine the ground brightness temperature. So what does it mean by the two-look technique? I'll tell you. Suppose this is the surface. So the satellite, so we have atmosphere over here. And the satellite, whatever the radiation that is being emitted from the satellite needs to travel through the ground and then reach the surface, right? So the atmosphere also interacts with the radiation that is coming. So in order to do this atmospheric correction, what the satellite does is that it looks at the surface directly when the angle is 90 degrees Celsius, and also it looks at the surface after making an angle theta with the normal. So now we have two type of measurements or two types of radiation that the satellite receives. One is the direct radiation. Suppose this is the so the radiation that is emitted by the surface that is received by the satellite is known as the brightness temperature. Uh, so it has one brightness temperature from the another view or when the angle is normal, which is TB1, and it has another brightness temperature when it is at a viewing angle of 30 degrees Celsius. When it makes an angle 30 degrees Celsius, now the brightness temperature TB2 or the radiation that the surface emits is TB2. That is the second brightness temperature. Now we need to find, so we basically need TB0. That is the TB1. Theta is 0. Yeah, theta is 0. Mm. So we basically need TB0, which is the actual brightness temperature of the surface. TB1 and TB2 are coming after the interaction with the atmosphere. So we basically need to correct the brightness temperature that the satellite is measuring in order to get the actual temperature, which is TB0. Now, in the question TB1, which is another view, gives the measured brightness temperature of 300 Kelvin. And viewing at an angle 30 degree with respect to the vertical gives another brightness temperature, which is 298 Kelvin. And the mean atmospheric temperature, the temperature of the atmosphere, which is given by 250 Kelvin, TA. TA is given by 250 Kelvin. What is the actual ground brightness temperature? We need to find TB0, which is equal to question mark. Now, based on the optical depth of the atmosphere, the brightness temperature changes. So, TB1 and TB2 are basically dependent on the optical depth of the atmosphere. Now, the equation given for TB1 and TB2. So, TB1 is given as TB0 into exponential of minus 2 plus Ta into 1 minus exponential of minus 2. And TB2 is given as TB0 into exponential of minus 2 sec theta plus Ta into 1 minus exponential of minus 2 sec theta. These are the two different equations. This has two unknowns, which is TB0 and tau, which is the optical depth of the atmosphere. Now, in order to eliminate tau, what we can do is we will we will take this Ta out. So, TB1 will become TB0 exponential of minus tau plus Ta minus Ta into exponential of minus 2 from equation 1. From this, we can write TB1 minus Ta is equal to exponential of minus 2 into TB0 minus Ta, or exponential of minus 2 can be written as TB0 minus Ta divided by TB1 minus Ta. This is the value of exponential of minus tau. Yeah, inverse. Or TB1 minus Ta by TB0 minus Ta. This is the value of exponential of minus tau. Now in the second equation, we have exponential of minus tau into sec theta. So exponential of minus tau sec theta can be written as, so exponential of minus tau is TB1 minus Ta by TB0 minus Ta. Sorry, TB1 minus TB2, no, TB2, no. Here I am just substituting exponential. We know what is exponential of minus tau. So I'm just finding what is exponential of minus tau sec theta. Exponential of minus tau sec theta can be written as exponential of minus tau raised to sec theta. So it will be TB1 minus Ta by TB0 minus Ta, the whole raised to sec theta. Now we can write what is TB2 after substituting exponential of minus tau sec theta with this value. So TB2 becomes TB0 into, it is exponential of minus tau sec theta. It will be TB1 minus Ta by TB0 minus Ta, the whole raised to sec theta plus Ta This 1 minus exponential of minus 2 sec theta. It will be 1 minus TB1 minus TA by TB0 minus TA the whole raised to sec theta. So TB2, if we take this TA out, we can write TB2 minus TA is equal to TB0 into, yeah, yeah. If you multiply this TA inside, it will be plus TA minus TA into the same thing. So we can write TB0 minus TA into TB1 minus TA by TB0 minus TA the whole raised to sec theta, right? Now this and this will, now we know the value of sec theta. Theta is basically 30 degree. So sec theta is basically 1.154. So TB0 minus TA into this and this will go. It will be 1 minus 1.154 and minus 1.154, which will be minus 0.154 minus 0.154 into TB1 minus TA the whole raised to sec theta. Now if we substitute the values here in the left hand side, TB2 is 298 and TA is 250. 298 minus 250 is equal to, that is TB0 minus TA, which is 250, the whole raised to 1 minus sec theta, which is minus 0.154 into TB1 minus TA, right? TB1 minus TA. TB1 is given as TB1 is 300. 300 minus TA is 250. The whole raised to 1.154, which will be 298 minus 240, sorry, 250 is 48. 48 is equal to TB0 the whole raised to minus 0.154 minus 250 the whole raised to minus 0.154 into 300 minus 250 is 50. 50 raised to 1.154. It will be 91.3. 48 divided by 91.3 is TB0 the whole raised to minus 0.154 minus 250 the whole raised to minus 0.154. 0.427. TB0 the whole raised to minus 0.154 plus 0.427. 0.952 the whole raised to TB0 to minus 0.154. So if you raised to 1 divided by 0.154, how much you are getting? Final answer. This is not minus, this is plus. 1 point. So 1 minus, okay, it is negative only, right? It is 1 minus sec theta, right? Yeah, it is 1 minus sec theta. So it is minus 0.154. Oh, I think this side can't do. Here, I think I made a mistake. It is TB0 minus 250, the whole raised to minus 0.154. So 48 divided by 91.3 is 2B0. TB0 minus 250 minus 250, the whole raised to minus 0.154. So 0.525 is equal to minus 250, the whole raised to minus 0.154. 0.52 raised to mm, minus 1 divided by 0.52, the whole raised to minus 1 by 0.154 gives you TB0 minus 250. It is 69.8 is equal to TB0 minus 250, which implies TB0 is equal to 69.8 plus 250, which will be 319. 0.8 Kelvin. Yeah, approximately 315 Kelvin is the answer. Did you get? 319. So approximately 315 will be the answer. Yeah. In, in the option, it is like 315 is the closest value. So 315 is then. Yeah, this is very lengthy. Um, that's why I thought I'll just solve this and then we will end it. It's a bit lengthy calculation. Because we have two unknowns. No, they haven't given the optical depth. Since we have two unknowns, that's why it's a bit lengthy. Yeah. Okay then. I think we will stop here today. Anyway, all the best for your exams. Do well. Yeah. Okay then. Bye. Thank you for attending. Yeah.